part of academia. I've been in industry, I've been in nonprofits, but almost always doing soft money research for NASA. I was a lead scientist on a proposal for a NASA mission, but I'm also a mom, I'm an oceanographer, and my kids tell me I don't really work because I'm just on my computer chatting with friends, coding, and listening to music. When they stayed home during COVID, they learned all about my work, and that had some downside. So I also, I send these robots in the center picture. I sent 2 of those up to the Arctic during COVID, and I've just been involved in oceanography and remote sensing for most of my life, and it's been really interesting. I also realized I've been a data scientist my entire career, and I think they call us oceanographers so they can pay us less. But most recently, I've taken a position at NASA headquarters, driven by some pretty dramatic life events. So the speed of science matters. I actually drove on the street yesterday with my mom. In California, where I live, every fire season seems worse than the last. And through the quick sharing of geospatial imagery, we're able to find out if our homes survived, and if they didn't. In 2017 was really, I live in Santa Rosa, California, and we had a fire just sweep through the town overnight. And Maxar was posting data on AWS through their open data program within 48 hours after the fire burned through downtown. I don't think we evacuated. I don't think we came back for 6 weeks after that fire. And just being able to see whether or not your house survived was just emotionally a really good thing. And for those that didn't, being able to start to move forward with the insurance process was a really big deal. This image is 1 block from my children's school. I drive by it regularly. In that fire, 6 schools and 3,000 homes burned. And talking about sort of the emotional impact at my children's school, every class had 1 or more children who lost their home, who just lost everything that night.
All units, Sonoma Lake Napa, multiple starts in the unit, stand by for fire assignment. For engine 1487, utility 1468, engine 1463, engine 5763, engine 1471, engine 1481, engine 19, station 15, transport 1447, 1443, Canocti 4, Canocti 3, vegetation fire, city of Calistoga, highway 128 across the Tubbs lane, Tubbs IC, stand by for response check back, 2146. All units, Snow Lake Napa unit. We have 2 major fires going in the unit. 1 on Atlas Peak, 1 in Calistoga, 128 across the Tubbs lane. As you come into Napa County, come up, and I'll give you an assignment.
Single engine 419. Can I have the IC designator for the Calistoga?
So you thought I was going to talk about open science, and instead I'm showing sort of traumatic movies about fires. That movie was the 2017 Tubbs fire, and at 4 a.m. We were woken up by neighbors, and we just stood in the driveway, and there was fire on 3 sides of us. There was no power, no cell, because all the towers had burned already. There was no Google Maps, no news, just every few seconds we could hear these massive explosions that turned out were propane tanks. And so we had 10 minutes later, we had the kids and the dog in the car, and we just fled past multiple fire lines in what we hoped would be a safe direction. And we knew that friends had lost their homes, and we hoped that they got out in time. And this event really put climate change and the impact on our lives in a really different perspective. In 2017, we had the Tubbs fire. In 2019, it was the Kincaid. In 2021, the Glass fire. We've evacuated 3 times in the last 5 years. And for us, this is what climate change now looks like. This ending shot in the movie was sort of a Kmart on the north side of town. And at the beginning of the movie, when that firefighter's just calling every single truck that they can think of in the area, just calling everyone for help, They told them all just meet at the Kmart on the north side of town because that was 20 miles away from where the fire was. And an hour later when they arrived, the Kmart was on fire and the neighborhood around it. And fires are just one example of a climate crisis. And maybe you have your own example. I know there's a lot of people in Colorado who've been impacted by wildfires recently, but there's also the drought and the storm surges and the famine and pollution and heat waves. Agencies and governments and disaster relief people, they use this data, they depend on this data in real time to save lives. And it's larger than that because understanding why and how these events occurs allow us to mitigate the impacts before they happen. And this is where open science really can play a role and can really help. We have to urgently change how we are doing science. And that means making data easier to access, sharing software, building cyber infrastructure that's open and shared. And as data scientists, we need to follow open science because there is a climate science imperative to do so, but also follow it because it expands who participates in science. And right now, we need more people at the table. We need a bigger table. And the speed of science really does matter. So for many years, my research was focused on transforming the photons measured by a satellite instrument into a measurement of ocean temperature. And I worked for commercial companies, and this was proprietary information. And most satellites carry several instruments, and even people working within academia hold their algorithms quite closely. For ocean temperatures for a single instrument on a single satellite, I knew of 10 independent efforts to produce the exact same ocean temperature measurement from the same photon observations. And now multiple efforts are really good because everybody catches a different problem, but 80% of the code development was identical. It wasn't shared. It was redundant, and that meant algorithms advanced more slowly than if the code base was shared and advancements were doing collaboratively. And errors in competitors' algorithm were sort of celebrated because that means that you got further ahead, rather than acknowledging that part of the reason they exist was a lack of sharing and strained resources. This development path, it impedes advancement. It's difficult to share, and it reinforces institutional privileges. It reinforces the privilege of people who are already in science, who are already doing science, have, and it sort of closes the door to broader participation. But this is how a lot of climate science still works. Many scientists run their analyses on local cyber infrastructure with compiler-specific operating systems in pretty unique environments with software restrictions. And this makes it really hard to work with anyone else. And again, it sort of reinforces these institutional advantages, especially when you're talking about software licensing fees. Only a small percentage of scientists at the top institutions, startups, companies, agencies have access to excellent cyber infrastructure. And it's really difficult for outsiders to gain access. And that makes it hard to share software, to share data, to share moving ahead, moving forward in science together. And that really limits who can participate. We also have so much of science behind paywalls. So restricting access to knowledge, again, it perpetuates sort of exclusionary practices and reinforces these institutional advantages where large agencies and institutions have negotiated discounts for publishing and access. And at a point, maybe you're sort of starting to see a pattern, but the way that science is being done benefits those who are already doing it. And you sort of have to, at a certain point, ask yourself, who is that and who is that benefiting? And we know that our vision of the world is colored by our lives and our experiences, and that comes into play as we do science. Our answers are shaped by our experiences. And I think I heard NASA's Dr. Zurbuchen say it really well, which is like, if you get 5 MIT engineers in a room, you're going to get an answer. It's going to be a great answer. But their training was all similar, and that answer might not consider all the different possibilities or be the best solution. And here are some examples of really great solutions that solve problems, but they work better for the community that designed the solution. I mean, heart valves and seatbelts have saved millions of lives, but they don't work as well for women. They just weren't tested on them. Voice recognition software, AI algorithms have racial biases. And voice recognition software really recognize the voices of men much better because of the training that was initially done. And that's evolved over time. It's gotten better over time as more people have gotten involved. To get to these right solutions, to get to these better solutions with broader impacts, we need solutions that work for everyone. And to get there, we need science where more people are able to participate so that the questions are different and the answers are more inclusive. And open science combined with not just cloud computing, but also HPC computing together are reducing barriers to participation. And so after these events, I really changed how I did science. It was a big wake-up call. And now I go to a browser window, I authenticate myself, and I open up an open source tool like Jupyter Lab on a hub with environments populated, like pre-populated with all of my favorite open source libraries. So I don't have to worry so much about the installation. I just select the environment, and then I can access NASA, NOAA, USGS, all types of data stored on the cloud and process it adjacent to that data store with my ability to scale my analysis as needed. And this is really easy science. This is science for everyone. And as someone who's been outside of large institutions for most of my research career, this really resonated with me and really made me think about how we could start to bring this to more people so that more people can participate in science. We know that data is being produced faster than most people can download it, and we need new tools, new ways of accessing data. Climate agencies are moving data onto the cloud, and that makes it easier to collaborate, reproduce, extend results, and access isn't bandwidth limited. So more people can do science, they can access this data for the first time. And data aren't siloed into a domain-specific archive, so you can access 40 years of global winds just as easy as 40 years of Landsat imagery. And this is really, for many people in science, the first time that this is possible. This encourages more interdisciplinary research and helps us understand how our environment affects our health. And all of this broadens who can participate in science and makes it easier to work with people outside of your institution or agency. Open software can be permissively licensed, public on GitHub with a community that builds and supports it. And this way of building software openly has changed how software is built. It's changed how we train new employees, because in some ways we don't have to, especially if we're working on common open source tools, using common open source libraries. You can just walk in and start doing research. That saves months of time, if not a full year. And these collaboratively built tools are more robust, they're inherently interdisciplinary, and they've really fueled this explosion of AI ML in our communities. And why AI ML might be the most visible example, across most disciplines, there have been advanced open source tools that is making science easier and more accessible. And there's just no doubt that this is speeding up how we do science and expanding our impact. So we also have, we can bring all of this together, the data, the software, the compute. And this is like that cloud HPC computing slide earlier. We can bring this all together on cloud and HPC-based infrastructure, sort of like a science data platform. They're an interface that just provides this user's access to the coding environment, whether it's on-prem, on cloud, on HPC. It looks the same no matter where it's located when you sort of bring everybody in through a Jupyter hub and then start a Jupyter lab. And this means that as scientists move between agencies, jobs, there isn't a need to retrain. And this has mostly been developed by the open science community, and Jupyter hubs are becoming the default tool for science and for science data platforms. I mean, in Jupyter, you can use over 200 different coding languages, you name it. But it's open and it's community accepted, and it looks like the same no matter where it's located. You can have access to different data resources, software libraries. I have hubs on Google Cloud, AWS, the Microsoft Planetary Computer, NSF Supercomputer. It really doesn't matter. I mean, I basically log in, I'm looking at Jupyter Lab, and in a few minutes I've cloned my GitHub repo and I'm off to the races. This transformation has been enabled by technology, and it's really just matured in the last couple of years for broad adoption. And that's really critical. We're at this point in history where this is possible, and it's possible to bring to a large number of people. this transformation in how I do science also made me realize that the funding agencies don't really reward this type of open work through their funding. Most companies and institutions don't necessarily value it. And I realized that maybe you have to be on the inside to start to really change some of these things. So I moved to NASA headquarters, and I'm now working to change how we do science so that we have bigger scientific impacts and we expand who's participating. So I've talked a lot about open science, and I'm just going to define sort of what it means to our project. We talk about open science, we talk about it being accessible. So open data, open software, open access publications. We also talk about it being reproducible, so using open source tools and libraries. And those two things really work together to make science more inclusive. It broadens pathways, it expands who can participate, and this is more equitable. And why should we do this now? Because like I mentioned earlier, we really have the tools now to make open science a reality. And this wasn't true 10 years ago. I think a lot of the developments were still being in the works, but now we've reached this point where it's actually possible. These advances in technology have created accessible, reproducible, inclusive science at a scale not possible. And part of that is through development of the HPC and cloud resources. There's a national and global momentum right now to move to open science as well, because it's really clear that equal and open access benefits the public. So why use open science to do this? Why not just go to cloud computing or just put your data up there? I mean, open science, because we're facing these really big challenges, COVID, climate change. We need more people. We need more hands, more eyes, more brains with really diverse experience to participate so that we ask the best questions, find the best solutions. And open science expands the applications, it increases the pace, and most importantly, it shares hidden knowledge and expands participation in science. This picture is from the movie Hidden Figures, and Katherine Johnson was key in putting the first man on the moon. That photo is from a movie a few years ago, but it's from a time almost 70 years ago. And when I look at that photo, it just really reminds me that when I look around science, it hasn't changed enough. We need to change something so that we have more people participating. And so our NASA's open source science is the activation of this open science community that is working to broaden participation. And it's doing that by recognizing that we need to meet people where they are. And that point may be different for everyone. Some people are really open about their software, but not their data, and some vice versa. So we just want to move everyone towards more openness and celebrate each step towards being more fully open. There's no box to be checked. There's no yes or no. It's just trying to encourage open practices and reward open practices. And so NASA started a new mission. It's called the Transform to Open Science. It's a $40 million 5-year NASA SMD mission. So it goes across all of NASA science, including Earth science. And the objectives are to increase understanding and adoption of open science, accelerate major scientific discoveries, and broaden participation by historically underrepresented groups. And we're doing that by, right now we're in the pre-phase A, which is NASA, mission language. We're preparing. 2023 is when we really kick it off and declare 2023 the year of open science, and just have a whole suite of activities. And during that year of open science, we are going to be working to co-develop and to engage and to energize the open science across the scientific community. And we have 4 main areas that we're working to do that in, because we recognize you can be visible and engage, you can try to share resources, but you also have to change the system that we're working in, the scientific ecosystem, by providing incentives and working to change incentives within other agencies and institutions, and moving towards openness by partnering with other agencies and institutions, and really changing the framework that we do science in. So first, the engagement. We're doing a lot of community building through outreach, monthly community forums. We're having a community panel this Thursday. I'll put a link to the chat in that. we're having a monthly forum this Thursday. We have a TOPS community panel, which is the following week, which is 3 days long, and that's a deep dive into all 4 of these areas. We have an email list, and we have GitHub with discussions enabled and a website. We're also doing conference visibility. So we're working with societies to create open science themes for their 2023 large meetings, for them to promote and launch a TOPS Open Science course with booths, events, workshops, plenary talks, and communications. So a lot of these societies do a lot of communications, and we want open science to be in all of those. With the capacity sharing and the resources, we're developing an open science curricula, which are 5 modules organized around a scientific workflow. There's a lot of open science resources already available online, and we're working to expand and co-develop with those, not just reinvent the wheel. So the first is the ethos of open science, and this really gets to the ethics because, again, different communities have different ideas and different norms, and starting that conversation early is important. Next, open tools and resources, GitHub, Jupyter Lab, Zenodo. Where can we put data? Where can we put things? How can we share things? And then we go into the specifics of how to share software, how to share data, and how to share results. And there's micro-badging along the way for each module that you complete. And at the end, there's a TOPS Open Science badge that will be available. That open science course will be on Open edX. It'll be interactive. It'll be free, public, open. It can be used in in-person, virtual events, and independent learners can just log on and do it. There'll be videos, quizzes, workbooks, and there's a fast pass option. So if you already know how to use GitHub and you know how to share software, you can answer a few questions and get that micro badge. We are requiring everyone to take the first module on the ethos and the ethics because we think that that's a conversation that isn't had enough, but the rest of the modules you can do fast passes. And having it on Open edX, which is a learning management system, an LMS, that allows us to track learners, the completion of modules, identify if there's barriers that people are experiencing, that everyone stops at the same point, and do data analytics. So it allows us to really try to build community around these modules. So we can see that people signed up for one, but they haven't completed the rest. We can sign them up for a virtual cohort that can support them completing the rest of the module. Because this will all be on GitHub, it's also the basis for in-person workshops. And we're going to incentivize the completion with these micro badges and then a big certification at the end, and have prizes, challenges, and boot camps organized around this. And we want to make it easy and everywhere with workshops at big meetings, workshops at science team meetings, and virtual cohorts. With the community development part of that, we're going to be calling for TOPS champions. So these are scientists to help teach the modules at events and act as open science champions and build community. We'll have Rosa's elements that will fund most of these elements. So we're going to call for cohorts, so engaging with learners through virtual cohorts. So we'll be having Rosa's elements that will ask for people to propose to do this. Also for institutions to host summer schools. And this is another way that we can broaden participation in science. So we'll have institutions selected that will do the open science modules. So in a 5-day science team meeting, the entire science team gets trained together in open science. And the institution brings in additional people to participate in the science team meetings so that we include new people who haven't been part of NASA science teams before. And the afternoons are science team business. So you sort of get open science and science team all done. We're also going to be looking to expand the curriculum. And I think this is where a lot of the tutorials that have been developed for this workshop would be great to contribute. So where everything's on a GitHub repo, and we'll be asking people about cloning things and trying to bring them in and building together. We'll be looking for hackathons. We're looking to partner with societies to create and manage open science prizes and awards programs. And this will be to reward leadership and progress towards open science and showcase the benefits. While the badges and certifications may be more of interest to early career professionals, we recognize that mid to late career professionals are perhaps more motivated by awards. So we have both. And we'll be working with societies as well and looking at our own to evaluate and update existing awards and recognitions to include open science activities as a reward criteria, and where possible to allow for team nominations. And I'd like to call out AGU here, who quietly, they didn't make a big deal out of this, but they updated their fellowship nominations. So if you want to nominate someone to be a AGU fellow, as of this year, you also need to include comments on what they do for open science and whether they're involved in open science activities. And it's steps like this that normalize open science and value open science, and the community will take their cues from that. As we move towards openness and we're moving towards the Year of Open Science, we want to recognize and reward open science practices. And we do that by looking within the NASA systems to update systems to increase visibility. And that could be within the proposal submission process, allowing room for software. Data management plans are already there, but software management plans that specifically ask about, in both of these, what open science activities plans you have. And then start to require the TOPS Open Science badge, because we do want teams doing open science. So maybe at first, just a little bit of your team, you have to have an open science lead maybe. And then as we get further along, that most of the science team is experienced in open science. And we know the results speak for themselves. Open science is transformative and it has huge impacts. This is an image of the first, this is Katie Bowman with the first image of the black hole that was done using Matplotlib and Python. The Mars rover used open source libraries. Here are, AI algorithms used to find illegal gold mining in Africa, then being applied in the Amazon. This is powerful science. And we really want everyone to get involved. We're looking for the community to co-develop by helping out on GitHub, joining the discussions, and advocating for open science within your institutions, companies, agencies, and community. And that way we can build these resources together. And I think we have time for discussion now, so thank you.
Well, I'm certainly very excited, and I have a bunch of questions. But there was a softball in the chat that Adam already answered in there, which is how do we get informed about opportunities that you're talking about, and do you have a mailing list that we can subscribe to? So I imagine that, Adam, we can throw a couple of those links in the chat, right?
Yep, so I put one in there to the TOPS website, and I'm not sure if there's others that you'd recommend.
I did the TOPS website, and if you go to the I'll put in the GitHub repo, because our GitHub repo has announcements about our community meeting, which is this Thursday, and that's open to the public. And then also our community panel, where we're doing a deep dive to really discuss the open science curriculum and our plans in detail next week.
Fantastic. So folks in the audience, you can either enter your question into the chat, or you can raise your hand and we can bring you up to ask your question in person. But Adam, I do believe you had a question to kick us off.
So we I guess started discussing this earlier, and how do you envision like getting other communities, other organizations like DOE, like ARM involved and collaborating on this? It seems like with 2023 being the year of open science, there's maybe a big amount of momentum we could all have towards going to open science. So how do you envision that?
Thanks. So we actually presented TOPS and the Year of Open Science to OSTP, the Office for Science, Technology, and Policy at the White House, and they were quite excited about it. So we presented it to their subcommittee on open science, which DOE, I believe, is part of, and they have proposed a sub-working group on the Year of Open Science, which is actually a really ideal way for us to collaborate, because memorandums of understanding between agencies take a long time and a lot of lawyers to develop. Using, I think, this sub-working group through OSTP allows us to create timely coordination among agencies. So on the agency side, I think that's the best place for us to work together. especially to do it quickly, since we start the curriculum development in about a month. And for everyone else, for the community, I encourage you to go to the GitHub repository. We have discussions enabled. You can ask questions, you could submit pull requests, and we're really starting to populate that website right now. A lot will be going up in the next week. Right now it's a bunch of README files, but we'll be getting a Jekyll website up there pretty quickly. And I think we need to co-develop, because there's so many experts on this out there. But the reality is that many of us in open science, once you sort of come to the grass is greener side, it's easy to forget that probably 90% of the science community is actually not there yet, or not comfortable sharing code or algorithm or data. And everybody from every discipline is at a different point. And so I think the more that we can start to use the Year of Open Science together to advocate visibly for open science and tell success stories is really going to help move more of the community over to open science so that we broaden participation.
And I know we have some DOE representation here in the audience today. It's fantastic to see them here. And so I kind of put it as a charge to the folks who are in the audience here. And I know for one, I'll be involved in this, that we really want to, whether it is direct or in kind, have this program and other areas in DOE very much embrace that Year of Open Science. We do have a question in the chat from Gupta, and they ask, do you have any suggestions, roadmaps on how to address the system constraints, such as things like paywalls? How do we work around the existing constraints to open science already posed in the community?
We are working with publishers directly and letting them know our plans so that they can prepare financial models that work for them. NASA is working towards their SPD 41, where there will be a requirement for open access publications. And while that may work for NASA funded researchers, they tend to be on the wealthier side. They're getting big NASA federal grants. So there was recently an article in Nature, I think about a month ago, that talked about exactly this issue, where it's 3 months of a professor's salary in the Ukraine to publish an open access publication in Nature. Yeah. I mean, $12,000 is nothing to sneeze at, even for a NASA funded researcher. It's a lot of money, or I guess it's 12,000 euro. I guess it's only $10,000 or something. No, I got that reversed. But how do we make it equitable? And so part of that is doing two things, I think. And one is first to work with the publications themselves to say, we are moving towards open access. Make sure that you have avenues for people who don't have large funding amounts to publish open access. We need that to be an option that you can apply for. And second, to recognize that while publishing in Nature is great and you get a lot of visibility and career credibility about that, science is changing quickly, and posts on Medium and publishing Jupyter notebooks and using Jupyter books to publish your research in an interactive way is becoming more and more the norm and more valuable. And I think systems will develop around that will provide avenues for people to share science. And I think that we need to find a way to recognize and value that as well. And there are some things that are beginning to start around that.
That's fantastic. I really want to actually highlight something you said there about the different mediums for getting scientific content out into the community. And you know, you come from an oceanographic background. We're mainly meteorologists and atmospheric scientists here. Working with the computer science community, it's almost a completely different thing across there, where preprints have so much more value there. And the idea of getting things out in shorter, more, I don't know, targeted contributions is that. And I can, you know, speak for the journal I'm involved with, which is Artificial Intelligence for the Earth Sciences. We're recognizing that as well and trying to help AMS and other journals kind of reimagine what an academic contribution looks like. But I do want to go on to another question just quickly in the chat. We've got 2 minutes.
I want to say
Yeah.
one more thing about that, which is this short, fast thing, right? So computer science started moving so quickly that the journals couldn't keep up. And then they went to this preprint model. We saw the same thing happen during COVID. And if we're able to expand participation in earth science because of climate change, I think we will see the same revolution in earth science.
I absolutely hear you, and when we need change there. But Ken asks, Kehoe says the Department of Energy has a different policy on sharing the Department of Commerce. How do low-level scientists best encourage the decision to open up software to the higher level decision making, to the funding agencies? How do we get them to value open source more?
I think that part of my movement to NASA headquarters was driven by this. There are so many constraints about sharing software, and every agency is a little bit different. And then when you get into funding external groups, whether it's universities or companies, you then have contracts, and you get into contract law, and whether it's a grant versus a contract, what are the patent rights in there? And luckily, the universities own the patent for all federally funded activities, as do most institutions, which you have to own the patent to be able to open sources. So that puts us a little bit further down that road. But I think for scientists, for us to advocate as much as we can to our people in management and people in leadership, what I hear over and over from people within, especially institutions, because government agencies have a lot of regulations, which I've learned a lot about this month. It's scary to try and do open source within a federal agency. It still just is. And we need high-level visibility and support for open science in order for scientists to feel safe and active in this area. And so many of the software release authorities have just completely lagged behind how open source development is currently being done, and the way that you contribute to other people's code, your own code, the way we need the software release, agreements to be updated completely to reflect how open science is being done if we want to be able to do open science. And that has to happen at the highest levels.
Oh, very well said. Especially, I like the bit about, contributing to other software packages and things like that, which if more people did that rather than rolling their own, having their own agency logo on it, that would be great. There's a question from Eric Tidd who says, Chelle, what technical support or centers of excellence do you feel are necessary to enable more scientists? For example, not all know how to use the technology across facilities and also in the cloud.
What I've found is that the more that we can, and you see this, I think, across coding, the more that we can sort of hide the data, we can hide the access, we can hide the infrastructure, the more that we get people to participate in science. And I think Jupyter has been leading the field in this, and there's a reason that it's becoming the default for science, is because it allows us to hide the infrastructure. And I really do. I'm not joking. I have hubs. I have to bookmark them because I lose track of all the different hubs I have access to. And it doesn't matter because I'm just using them for compute and maybe some local data stores there. And a lot of times I'll just, run something on AWS that I know is part of their AWS public data program. And then I move over to Microsoft Planetary Computer because I want to use some of the GOES data that they have in a better format. And that making the infrastructure invisible is a real goal. And I think when you talk about technical support or centers of excellence, I think what we need to support is the open source community and their continued development of the abstraction of how we do science so that scientists can stay scientists, but still access all these tools and easily collaborate with other people in different disciplines. And it's really amazing. You shouldn't have to know whether you're on an HPC or AWS. You shouldn't have to know if your data is in GRIB or NetCDF. You should just be able to say, I want satellite data, and then be a little more specific. I want rain data over Santa Rosa for the last 5 years. And we want something that is easy to use. And I think Google Earth Engine, in some ways, though it is a commercial product, it's sort of the vision for the future, where it hides a lot of the code that's necessary, the infrastructure that's necessary, and it starts to make it through just SQL calls really easy to do incredibly powerful computation. And when I talk to different communities, the broadest participation that I see are the people using Google Earth Engine because they've been able to do that. And I think we need to do that as federal agencies as well.
And a federation of federal agencies at that. It would be awful if we ended up with a siloed solution.
Yes.
So we have 7 more minutes left. That's right, isn't it, Adam? We go to 10:02 here.
Well, we can technically go the whole hour if
right.
So
I've got some questions I'm going to ask in a second, but anybody else, please raise your hand or enter another question in the chat. Chelle, my question specifically relates to compute. Something I've become increasingly aware of in the DOE space is that we tend to focus on huge problems, basically where you need a supercomputer in order to really get the attention of our leadership computing facilities, when it really feels like that there's so much more that could be unleashed with 64 cores in a Jupyter Hub, basically. So what's your take on mid-range to high-level supercomputing and equitable access to it in the open science space?
Yeah, I think that there are things that we will never be able to do on the cloud. And I would say that we can, by expanding equitable access to cloud computing, that we can reach probably 80 or 90% of the scientific community. But there are 10% that really need high performance computing. And for them, I think that HPC supercomputers are going to be the answer. And we have to, as a community, I think, figure out how to ensure that those HPC centers don't become new silos of data. Because if you're running the model on that and create massive amounts of data, but not I think part of these supercomputers in HPC has to include some form of both data access and compute access for the community, so that we make it a little bit more equitable, but that also we really need to make sure that whatever results we have, if you're going to be publishing, you have to have them available to the public. So we have to make sure that we're providing access to the results, and that's a formidable challenge.
It begs the question: if you need a supercomputer in order to run the code, is the science ever really reproducible, or is that more of a goal there?
Yeah, I think reproducibility, it gets more and more complicated, especially when you get into the AI ML, and just running it on different processors is going to give you different results. Yeah. And that's an area that there's a lot of work on. And we can, again, it's this spectrum. We may not be able to reproduce it perfectly, but as long as we can move towards the goal of reproducibility, that's the direction that we want to be headed in.
Awesome. All right, anybody else with any questions, please throw them in the chat. Adam, did you have a question?
Yeah, well, not so much a question. I was actually hoping we could get Geary up here potentially. So ARM has a Jupyter Hub instance that is requestable through an access request form.
Gary's beaming in.
Gary's having trouble materializing into his physical presence.
All right, so give me a second.
That's quite remarkable, Gary. I don't know how you managed to do that.
Yep.
Yeah,
Geary, so with the Jupyter Hub resources we have, we've been able to scale it up fantastically for this workshop. It's available. I believe there's also going to be a Jupyter Hub instance on our HPC resources as well, like Cumulus 2, right? So
yes.
Do you just?
In fact, we just released it earlier this week as a beta testing. So all of our HPC users are able to access that right now.
Okay. So how do you see, I guess, this going forward? Are you looking to expand capabilities with Jupyter Hub, expand access for all of our users there?
Absolutely, Adam. In fact, we are drafting an ENG for that. It's a nuance, within ARM. But so I guess like our strategy is allow our users, either HPC or our regular data servers or compute servers, to easily access using the Jupyter Notebook. And I'll reflect on both sides. One, for our regular users who wants to quickly access Jupyter Notebook and do something. So Monica and we were talking about essentially allowing registered users as a way to access Jupyter Notebook by requesting through the data discovery. So it will be a seamless experience for our users. So you go to data discovery, you ask for, okay, this is the data that we want from ARM. By the way, I want to check this data or create some script using your Jupyter Notebook. So that's one way. And the second one is what you're asking, HPC. So with enabling Jupyter Hub on the Cumulus cluster, so this is our the newest HPC cluster that we put it operational a couple of weeks ago. So this will allow users to quickly request and access the Jupyter Notebook and our Jupyter Hub, and then they will have the full access to our 3+ petabytes of data. And the idea is they will use this data to develop script, and then when they are done, and if they want to run a long-term analysis, with one more click, they will be submitting the jobs to our HPC using Slurm and all. So all those would be seamlessly integrated. So user doesn't have to worry about going into HPC and trying to figure out all these. So it'll be like from their own laptop, they can almost do everything. Of course, they will have to apply for Jupyter Notebook account, and we will closely monitor the activities and all those things. But I think this will remarkably improve our user experience.
Yeah.
Do you have to be at DOE to access this?
Absolutely not. Absolutely not. And so the HPC, it is, I mean, as part of ARM is a national user facility, right? So HPC computing is also part of the ARM facility. So that means anybody can request or submit a proposal. Yeah. If it is a major proposal, they will. I mean, we have a process that user use to submit their proposal, and we review and provide access.
And DOE recently, through several initiatives, has actually started to provide support for underserved institutions to engage more closely with programs across that. And so with that funding that's coming out of a sister program to ARM, the ARM facility is spinning up to try to work out how we best engage with those folks, because we do have this really interesting issue, and this has been discussed at several levels here, about, again, equity of access. Because sometimes it's very difficult to even work out what you need to put in a proposal. Let me just quickly check. I saw a hand go up. Dan. Oh, actually, first I just want to ask a question from the chat. There's actually a question from the chat first from Alicia Karspek, who says, Chelle, can you speak to the issue of storage costs and needs in the open science paradigm? Lack of long-term storage can bottleneck model-based science when there are requirements of keeping data available indefinitely. Or when are there?
Yeah, it's expensive. And I think a really key part of, I think models just, I used to say that models produced so much data, it was overwhelming, but we have NICER coming online next year, which is going to be producing 30 petabytes per year of data, the satellite. So I think we're all getting into these big data worlds. So the way that we've been thinking about this is that at the time of funding, there's a very clear plan for your data management, that it is funded for, it is described. This model result is expected to be so important that we do need to keep it available indefinitely. or just stating this model result we expect to be, useful for the next 5 years. We're budgeting for that now. And at that time, it will be put either into glacier storage or deleted because it will be overrun by other results. And we just have to be very clear. We can't save all the data, and we're going to have to make decisions and then just be honest about them and at the very beginning and try to do the best we can about funding the important things to save.
Right, and there is actually a an EarthCube meeting in North Dakota in July, led by Doug Schuster and a couple of others. I'll be heading up there, and the literal question that Doug posted me is something I've been playing with a while, which is, and it literally, it's what about model data and reproducibility of model? What can you store? Like, for instance, if you store the initial conditions of a model and then the code for the model, would that be enough for reproducibility? So I think you're right there, Chelle. It is very much a an active science question there. What does reproducible model data look like? And Dan, you had your hand up, mate. You want to rock on?
Yeah, sure. Thanks, Chelle. It was for a great presentation and a lot of food for thought. I wanted to maybe expand, or at least ask you a little bit to expand on, the efforts that it sounds like NASA is engaging with a mission in 2023, and kind of how that works across, or how the thinking is, how it would work across agencies. And the reason I'm asking that is because I'm engaged with a field campaign in the Colorado Rockies to understand kind of the dwindling Colorado River water resources, and there are a lot of agencies involved. DOE is definitely involved. NOAA is, USGS, NASA, U.S. Bureau of Reclamation, Denver Water. It's a Upper Gunnison. So there's a lot, and I'm seeing a lot of territoriality, so I guess especially we've been trying to work and trying to see, okay, how do we make these data available so that a researcher who's unfamiliar with all of these things that are happening can get at all of these data and know where they are, know that they exist. And it's pretty balkanized. So anyways, yeah, appreciate your perspectives on this.
Dan, thank you. And thank you for trying to make the data available. I was running some robots up in the Arctic that I was talking about earlier, and I thought, oh, it'd be great. We can get all this cruise data from the oceanographers who've gone up to the Arctic, right? And it's like, I have that meme in my head where it's like the Star Wars meme where they're like, right? This is how it's supposed to work. And people just ignore my emails because I think they plan on dying with that data on their hard drive. So I think what is incredibly important, and what you just pointed out, is we have to figure out how to do this together. We can't have NASA say everything's open and all of our funded scientists are going to create one data management plan that's going to be different than the NOAA scientists or the USGS scientists, or have one agency pushing in one way or another way. I think we all need to figure out how to do open science together and advocate for that together, so that, especially for field campaigns, I think those are the ultimate. Well, okay, I'm an oceanographer, so I like, that's sort of my area, but it's hard to get people to share, especially field campaign data, if you're involved in field campaigns. Now, modelers would say that, like every community I talk about, there's different norms around data sharing. And I think that this is part of where having federal agencies all adopt some open science agreement, open data agreement, so that when these field campaigns are first proposed, there's a baseline that everyone has to adopt, and that it includes funding for that, because you can't just say make your data open and not have it be fair. And so findable, accessible, interoperable, reproducible. You have to make sure that people have funded for and planned so that their data are accessible, reproducible, available, and that takes time and money. And some people would argue, well, that's time away, that's money that's not being used for science. But I would argue that this is your job as a scientist, is to communicate your results, and that communicating your results is probably the most critical part of your job.
Can you just to follow up? I know that I saw another hand raised, but I just to follow up on kind of how you see those that adoption across agencies, how that would how that would be advanced and the efforts that have been advanced so far on that, and also the things that have where that advancement has needs a little bit more pushing.
I think that's where working through this OSTP sub-working group of the subcommittee is a place to try and start using 2000. So we're trying to basically use 2023 to start these conversations between different agencies to start to move forward, because it's not just as simple as saying, okay, we're going to everybody's funding announcement is going to have a requirement about open data. Your contracts people also have to understand that that needs to be written into the contract. Also, when you're writing the proposal, you have to be very clear in what you're asking for. What are you asking for? Licenses? Are you asking for fair data? Are you just asking for it to be on a FTP site? So we all need to start moving forward together, because with federal agencies, nothing happens that fast. But if we can use 2023 to get started, that's what we need. That's what we're trying to do, is just like try to just set a point that we can start working together.
Right. Madam.
Well, no, I was going to follow on Dan's question here, but we really only have, less than a minute left. So, I just really, Chelle, if you have any parting words of wisdom or thoughts, before we move on to the next. This was great.
Thank you. I just want to say that I was the co-chair of the open source software policy options for NASA by the National Academies. And I remember early on, one of the things that we read was some of the software policies that DOE had, and they were really setting the path forward. And they were much ahead of a lot of other agencies. And I really would hope that they'll be part of this year of open science. So thank you.
Thank you. And I'll point out, so we have 62 people online here who've come in to hear about open science. So definitely, as you move forward with these subcommittees and so forth, please reach back out to us, because we're enthusiastic. And thank you so much for your time. So round of applause.
Thank you.
Adam, back to you.
All right.